Hello, community. So great that you are back. Today, we discover chaos in multi-agent system. We have a new research paper that tells us, hey, our multi-agent system, you know what? We use them for real complex tasks, no? Multiple agent, and if we analyze them, their performance improvement remain minimal. And here we have a beautiful new study by UC Berkeley, and they tell us, we looked at multi-agent system here with GPT-4 Omni and Claude 3 and the popular and whatever, and the performance is not famous at all. And you might say, but wait, multi-agent system are increasingly explored here in all the domains, software engineering, like here, open hands, or we go in scientific research. I even have a particular video on this topic, no? Or if we go to Manus or Open Manus AI now, where we have this is the breakthrough now. You know what? We encounter that in a network of agents, there's chaos because some agents are left alone without any task. Then we have subnetwork of agents. We have isolated islands of agent. We have agents that only communicate with each other and agents that are just dead. So, this looks like failure. Isn't this fantastic? So now we have a chance to optimize our multi-agent system topology. But hey, let's be scientific, no? So when we open now this video, we have to start with a definition. A multi-agent system is defined as a collection of agents that are designed to interact through a particular orchestration, enabling now, hopefully, a collective intelligence. And you know what? Our multi-agent system is structured to coordinate the efforts, to enable here a task decomposition, to perform here some parallelization, have context isolation, specialized model ensembling, and diverse reasoning discussion, and self-reflection, and react, and self-improvement, and you know it. So, what is our spark of genius? We need to develop a taxonomy of multi-agent system failure. Now, if I tell you we, I mean UC Berkeley, and I'll give you the result. Data discovered we have more or less three particular modes. Poor specification in the system design, poor agent coordination, so we have an inter-agent misalignment happening in our systems, and simply, we have no quality control and no task verification, and the little agents are just doing whatever they want to do. So, they did a beautiful experiment, 151 traces and whatever, but I just want to give you the core, the main result. If you look at this here, pre-execution, execution, and post-execution of the inter-agent conversation stages, you see what we have. We have agents that disobey the task specification. We have agents that disobeyed their role specification. If you say, hey, now you are a physicist or a mathematical expert, or you are, I don't know, a code expert. We have a loss of conversation history. Suddenly, a sub-network of agents just forget the history, what they already achieved. And then we have an unawareness of termination conditions. Some of our multi-agent systems just want to go on indefinitely. Inter-agent alignment. Suddenly we have a conversation reset. They decide, okay, folks, we just start new, né? We have failed to ask for clarification. One agent doesn't understand what its task is, but instead of asking here anyone, hey, what am I supposed to do in this network? The agent just starts to do whatever the agents think is the right thing. We have a task derailment setting in. What a surprise, né? We have information withholding. Can you imagine a little AI agent looking at another AI agent and telling the other one, I'm not gonna tell you my result. Sorry, you have to find out yourself. You ignore the other agent's input. I mean, is this believable? This is so human, this behavior. We have a reasoning action mismatch. And one of my last videos showed you how we can train here in a reinforcement learning that we have if the autoregressive next token prediction, we have a reasoning token or we have an action token. They just mismatch everything. Then we have premature termination. The system just thinks, okay, that's enough. That's okay for today. Let's go home. we have an incomplete verification. We have incorrect verification of systems. Yeah, who cares if it's right or wrong? So, hey, I have to tell you, I love my little AI agents. And it is amazing that UC Berkeley took the time, said, hey, let's look at what is going on inside of our multi-agent system. So, of course, they had to do an evaluation. Well, AI automated evaluation. No? What we have, LLM as a judge. Is this the perfect way? No, of course not. But at least it uses OpenAI's O1 and not some old llama model. And to validate the pipeline, they had to cross-verify this. Ah, yes. And my goodness, they used human experts here for this 151 traces to discover what's going on and if OpenAI is correct. So you see, evaluation, cross-verification, and then we discover what's happening. The nice thing, UC Berkeley say, hey, full open source, I'll show you at the end of the video, all annotated conversation traces, all LLM as a judge evaluation pipelines, all detailed human expert annotation, whatever. What is the result? The findings suggest that this, what's going on in our multi-agent framework, is not an artifact, is not a coincidence, is not a hallucination by one agent, but it is rather a fundamental design flaws in our current multi-agent system. Great! We have some new research. I'm loving it. They tested it on different agentic architectures, an assembly line, a hierarchical workflow, a star topology, an agentic framework. Go wherever you want. Thank you, UC Berkeley. So let's come to the core of this. If we have three classes, let's have a look what's happening so that we are able to find solutions. So the first class, specification and system design failure. They discovered that the failures arising here in this architecture by a poor conversation management of our AI agents, unclear task specification for our agents, violation of constraint, beautiful, like little minions, or an inadequate definition to the roles and the responsibility of single agents. Let's look here at the violation of a task specification. Simple example. You ask here an AI to have a two-player chess game now, and now the AI decides, instead of the human chess notation, the AI decided to come up with a two-dimensional grid notation that is incompatible to the human chess notation. You see, not satisfying the initial requirements of the game. The second one, the inter-agent misalignment. You have failures from ineffective communication between our AI agent, a poor collaboration, conflicting behavior among our AI agents, our little minions, and a complete derailment from the initial task. I would say, hey, this is here on the edge of a chaotic system. So if you look here at an example, you have agents withholding information from the other agents or to the other agents. So let's say a supervisor agent instructs here, let's call it a phone agent, to retrieve some contact information using here the email ID here as the username. Now, the phone agent, after reading the documentation and finding out all the correct username, should be a phone number, still proceeds with the wrong credential, leading to an error. So, if only the email is given, then the next agent takes the email as a phone number. Now, I know what you're going to say. Yeah, okay. There are so many solutions. Yes, I know. But they are not in place. This is the beauty. Let's have a look at task verification and termination. Failures result here from a premature execution, termination, as well as a complete insufficient mechanism to guarantee the accuracy, the completeness, and the reliability of its interactions, decision, and outcomes. I mean, you say, hey, wow, we really have to learn a lot of, no? For example, in the chess game implementation, if we have a verifier agent, that's great, no? But you know what? This verifier agent decided only to check if the code compiles correctly without running the program afterwards and ensuring its compliance with the chess rules. So we do have a verifier agent, but it falls short here of the complete responsibility for a verifier agent. So our little minions, our little AI agents, if they work together, Wow, there are some key mistakes. So let's have a look at this. We have an ambiguous or incomplete task definition. Then we have role misspecifications, agents acting beyond their assigned roles. Where little minion says, hey, today I want to do something else. We have a loss or a misuse of a conversation history, so of the logs. We are ignoring constraint, or the agent says, hey, today I don't care about my instruction. I will do something else. We have agents ignoring or misinterpreting each other inputs. We have agents that are withholding critical information to the next agent because, hey, today is Tuesday, so why not? Failing to ask or provide clarification. If an agent is not sure about the format or the task at hand, it fails just to ask somebody to specify here further details. It just goes on to do whatever it likes. We have inefficient, repetitive, or irrelevant interactions going on between the network of our agents. And we have a weak, incomplete, or a complete absent verification mechanism causing undetected system errors. This is the state of a multi-agent system, and hey, wow, our researcher at UC Berkeley, amazing insight. I was not aware of the current state. So let's have a look at the fact. This is here the publication I show you, March 17, 2025. This is from UC Berkeley. Why do multi-agent LLM systems fail? And they come up with some beautiful explanation, only looking at multi-agent systems. Now there's another beautiful dimension to this whole story. Because you know what? In 1986, I think, in UC Berkeley, they developed here a very specific experiment, a very famous experiment, HRO. So this is a highly reliable organization. And even at that time, they said, if we have large-scale technological system, we have a complex of a human interacting with different machine. In 1986, it was real mechanics. And they said, we have to have reliable system. We have to analyze the dependability of the human that interact with the machines. So they came up with this beautiful study, and they said, let's examine here how does it work together and predict the institutional behavior of highly reliable organization. Think about here if you have here flight control. Think about a nuclear power plant. Think about, a fighter jet. You have these systems to be reliable. And this is the study. Unfortunately, it's behind a paywall. I cannot show you the real study, but the title was Research in Nearly Failure-Free, High Reliable Organization. And this was published here May 1989, an IEEE transaction on engineering management. But all of this is behind paywall, so unfortunately I have no access to this. But I can tell you a little bit about the content, what they found out. They found out that in emergencies, let's say on a ship, decision-making migrates to people with the expertise. Regardless of their hierarchical position in the organization, think about a military ship, we have immediately decision-making. All the people look to the expert in the field. However, this is completely different in routine operations, because in routine operation, they found that decision-making is absolutely hierarchical. You ask the boss, and the boss will decide for you. In emergencies or high-tempo operation, this symmetry breaks. Management by exception. Normally, let operational decisions be made closer to the decision implementation side. And the role of the manager, they should focus on the bigger picture, and develop the strategy, whatever. However, this is not going to happen. Or let's talk about continuous training. So if you are responding to unexpected problems in your organization, in your hierarchy, in your team structure, this works best if you build interpersonal trust and a credibility among the co-workers. Without those, you don't have a backbone to fall back to. Plus, they found safety-critical information communicated You need a number of channels. 1 or 2 channels is not enough. You need a variety of communication channels. So in an emergency situation, the data reaches the right person and they say, yeah, nuclear-powered aircraft carrier, for example, they have 20 different communication devices to make sure that this is gonna happen. Plus, we have a high redundancy rate. No? We have internal cross-check of safety-critical decision. No? For example, here this buddy system. No? You have always a second crew member that knows exactly what you know, so you have a redundant data storage. And now comes the beauty, and now UC Berkeley tells us, you know what? We had looked at this HRO experiment at our insights, and we found we can apply the insight from human organization and the failures humans do in our network. More or less, something similar is happening now in artificial intelligent agentic networks. And I was laughing when I read this because I said, oh, it's so beautiful, no? Now, they said, hey, we have tactical approaches to solve this, no? Specific failure modes can be avoided, we can improve the prompts, we can optimize the topology of the network of the agents, we can improve here piece by piece the conversation management, but this would just be a tactical solution. What we really need are structural changes, a strategy that really goes to the root of the problem. And they identified, for example, a critical role of the verification process, and we need verifier agents in our multi-agent system. And I thought, this is interesting. I always thought that an AI system would provide here the correct answer, would provide factual information. And now it turns out, maybe. If the AI system is in the right mood on a Tuesday morning, maybe, but maybe not. So, massive verifier are required. Plus, interesting to read that they recommend here aligning here our multi-agent system with some reinforcement learning. You remember my last 10 videos on this channel was only about reinforcement learning. Now it pays off that you watched all of those videos. I found it so beautiful. And an example, we have an AI system and we have here a chief product officer AI agent. No, because yes, of course. You know what? This chief product officer AI agent simply bypassed here the CEO, also an AI system authority, and this chief product officer made a decision that should have been done by the CEO or a group decision. But my little minion, my little chief product officer, my little AI decided, hey, I decide about this. And maybe I tell somebody else or maybe not. And I ship this product. Amazing. Or AI agents here just ignored past instruction, leading to some redundant steps or a loss of context. My little minion said, hey, why should I care about the past? I'm looking forward into the future. So what we have, a lack of clarity in the rules that we assign to our AI agents. And this simply leads to rule violations. This means an AI agent improperly adopting tasks that are not assigned to this specific agent. But the little agent says, hey, today is Tuesday, so I do this. We have to take care that this is not going to happen, that we detect it and we correct it. And you might say, why is this happening? Is it hallucination? Is it just because the probabilistic distribution just shifts a little bit? No? It's happening and we have to take care because otherwise we are running into chaos. And what Berkeley did was mapping now the insights from the human organizational failures that we have also in our organization, in a company. We can map this, what we as humans do wrong in our communication process in a company. We can map this one-to-one to multi-agent AI systems, and I love it. So, human organizations fail despite having individually competent members due to a flawed organizational structure and flawed communication patterns. Now guess what? The same holds true for AI agent networks. They found here mass fail due to the rule specification violation, agents overstepping their assigned roles. This mirrors here in the human case here, the extreme hierarchical differentiation in human organization where unclear authority leads simply to mismanagement, especially in emergency situation when you don't have the time. Or failure to clarify or communicate effectively. So I'm loving it that we have now this mapping from all what human can do wrong, exactly AI agents do wrong. So in general, to my absolute surprise, because I thought multi-agent systems are proven, validated, verified, they are great, now we discover, if we look closer, that they fail. So if the first hype is gone by new, Manus or Open Manus AI system, the deep research does everything for us, and we discover, there's a lot of problems in our AI network, like I showed you in this port topology, port network activation. We have group of agents that only communicate with each other, and so on. So what we do, we have to find solutions, no? Tactical approaches are now clearer role and task definition. So we do have to precisely specify each and every agent role and the expected interaction. This helps to minimize the confusion and the boundary violation. We have to implement structured conversation patterns, no? Pythonic. We have to enhance here the verification on all and every layer. So we have to go for self-verification, system verification, communication verification, everything. We cannot rely on the agent itself. Structural approaches, 4 points. Use standardized communication protocols. Formalizing here the agent interaction. Also, you think it might reduce the creativity of the agent. Sorry, up until now, we need it. Just go with structured information rather than natural language protocols because, my goodness, even AI agent cannot understand other AI agents. Probability confidence measures. Assigning confidence level to the output of an agent enables here the complete system to pause and reconsider decision when suddenly all the network of agents see, hey, our confidence level is going down. So similar when a human decision making, we have an uncertainty in the management responsibilities. Reinforcement learning based for the further fine-tuning, for the alignment of our agent, they say is important. So to reinforce the correct role adherence and the collaborative behavior can lead to a higher overall system robustness and an agent adaptability. Plus, and they stress this here, comprehensive verification and validation. Do not trust any AI agent. Do not trust any LLM, any VLM, any VLA. We have automated verification methodology on all levels on the system. Domain-specific testing, symbolic reasoning, systematic checks significantly reduce the error rates of our system, similar to a quality assurance practice we have in the human organizations. I'm just reading this and I'm smiling here. I think, unbelievable. Those little AI agents, our little minions, they are so human. What a coincidence. So what are the final recommended principles that I would like to give you on the road if you build now the next robust multi-agent system? Clearly structured task and role specification. Rigorous verification mechanisms at every single stage. Standardized communication, clarification protocols, agent specialization and modular design, adaptive learning, and please use reinforcement learning-based optimization, probabilistic decision. Confidence management is an absolute necessity. I hope you enjoyed it. I hope you had a little bit of fun. You have everything open source by UC Berkeley. This is the GitHub repo. You have all the traces. You have all the tests. You have all the assets. You have here for the LLM judge pipeline, the Python programs. You have everything available. Have a look at the data. Have a look at the programs. Try to understand the amazing spectrum of failures that can happen within a multi-agent system. And I know everybody is trying to build the best multi-agent system, but just be aware, whatever theoretically could go wrong will go wrong at a particular point in time, at a particular complexity of your query, of the human query. And it is amazing how we have now to redesign our multi-agent system. I hope you enjoyed it. I hope you had a little bit of fun with this video. And if you subscribe, I see you in my next video.